Okay, shall we start? Okay. Today I'm going to talk about some static and dynamic properties of confined fluids. It's a confined binary liquid mixture. And since I already explained to you the basic features of confined fluids yesterday, the inhomogeneity, density fluctuations and all, so I'm going to skip that today, but in places where it's relevant, I'll repeat it once again, yeah? So, yes, the main idea is that, like I drew there, so you have two parallel plates, two confining walls, and you have a binary fluid in between, yeah? So say it has A and B type of particles, and then these, the walls preferentially attract one of the two components of the fluid, so you will have surface adsorption layers forming like I was explaining yesterday, and the question is, if I look at different static and dynamic properties of this fluid, how are they going to behave, yeah? Now the thing is, if you have a symmetry breaking surface field which you are imposing on the walls, it's going to break the translational symmetry of the system. And so clearly this is going to have effect in the different quantities that you look at. So that's what we will study in different situations. Once for the large separation between the two walls, and in certain cases for small separations where Casimir forces become important.
But you don't need fluid outside. You have fluid outside also or not?
No.
Only inside.
Only
because
inside.
the usual Casimir, I thought, like you look at the energy, but
the pressure difference, yeah.
But the energy is like you also have to take account of the outside.
Yeah, I mean, that's basically in a way of just to defining how you define the bulk pressure. So you can either have a fluid and you put a slab, or you can put it in between two slabs. As long as you are defining the bulk pressure and the background pressure correctly, it doesn't matter. It's just a definition. Okay. So this fluid is going to be close to critical temperature of a second order phase transition, a liquid-liquid critical point. So in order to explain that, I thought first it's good that if we recap some of the things which are relevant for bulk critical phenomena, because as we will see, those will be relevant when you are studying the surface properties as well. Yeah. So some of the things which I'm going to talk about, I mean, I'm sure all of you know it, but let's just recap those things, just for the sake of brevity. So we know that if we look at the phase diagram of a binary fluid mixture, this is the temperature axis, and here is the concentration, which is defined as the ratio of the number of, say, A species divided by the total number. And if you look at the phase diagram, it looks something like this, where we have a critical point, and then this is the critical concentration of the fluid. Now, close to this critical point, basically, the fluctuations of the system become very large. In principle, they diverge at the critical temperature. And what it means is that if you look at the fluid, so basically you have some correlated blobs which are forming in the fluid, and the length scale over which they are correlated, that's dictated by the correlation length, okay? So this is diverging at the critical temperature. So it does so as the bulk correlation length goes as some amplitude times the reduced temperature power minus nu. So my epsilon here is actually the usual E minus Tc by Tc. Similarly, if you look at the other static quantities like the susceptibility, we will have chi 0, epsilon power minus gamma, and then if you look at the order parameter, which is basically the difference between the concentrations of the two species, that follows a singular behavior, and it vanishes at the critical point, which you can appreciate from this picture also. Like you see, as I'm getting closer and closer to the critical temperature, the difference vanishing, and so the same thing which is being depicted by captured by the critical singularity. So as you see here, we have some critical amplitudes, and then we have some critical exponents, okay? Now these exponents are known to be universal, and I will explain what I mean by that. So what it means is that the values of those quantities, they do not depend on the material specific properties or the microscopic properties. So as long as you are in the same space dimension and you are taking the range of interaction is the same, the exponents are going to be the same. So for example, can you see if I write here? Okay. So for example, if we take, say, the Ising, okay, so the Ising universality class in 3D, which is a short-range interaction. And what do I mean by short-range is here, if you look at the interaction potential, if it decays faster than 1 over r to the power d, so that belongs to the short range, and otherwise the other one, yeah? So if you look at the Ising universality class for 3D, we know that the exponents, so the values of the exponents are known. I'll just write them down here because we will need it for the surface part as well. Okay, so this is about the static quantities. Now, the thing is, this correlation length that I'm talking about, that it's diverging at the critical point, so this will have effect in the dynamics of the system as well. And that's because, so when you look at a system, it's relaxing, okay, it does so over this correlated blob. And so if this is diverging at the critical temperature, the relaxation time will also diverge, okay? So, similarly, if you look at the dynamics, if you look at different transport quantities, you see singularities there as well, like the relaxation time, tau, diverges as it approaches the critical point. And then if you look at different transport quantities, for example, say if I look at the diffusivity, the mutual diffusivity, so this is the same quantity which I was talking about yesterday, which shows ballistic and diffusive motion. If you look at it, it shows a critical singularity, and at the critical point, it vanishes, and that's what you see here. So basically, at the critical point, the correlation length is becoming larger, and so it's at negative power, so the DAB is essentially vanishing. Then if you...
Now you are looking at Q.
This one?
Q to the minus
yeah, so Q is like 1 over xi, I mean the wave vector. Yeah.
You're looking at tau as a function of Q and at the critical point. Also depend on this other epsilon.
So let's put it this way. So if you look at the shear viscosity, so when you have the dynamics, which is becoming very small, the viscosity will diverge. And if you look at the shear viscosity, it shows this behavior. Now, when you have fluids, which means if you have hydrodynamics preservation in the system, which means mass, momentum, and energy conservation, that is also known as model H dynamics. If you look at the Hohenberg-Halperin nomenclature, and the values of the exponents are Z 3.068, XD 1.068, and X eta 1.068. So these are some of the things which one observes in bulk close to the critical temperature. Now, the thing is, so what we want to study is to, we have this confined fluid, and then we want to quantify its different surface properties. Now, in order to do that, it's important to have first an understanding of the bulk parameters. And why this bulk is important is also because we want to study the Casimir forces. So maybe it's better I just tell you why the bulk is important here, because so we wanted to study the dynamic properties of Casimir forces. And to do that, we needed to do molecular dynamic simulations, okay? And when we started the work, so basically there was no earlier MD simulation studies of Casimir forces. And if you want to calculate this Casimir force, you need to have an idea of the bulk pressure. So for that, first you have to come up with the right model with which you can capture the Casimir forces, and you have to quantify the critical behavior of that model fluid, because those bulk amplitudes which will be relevant for the study of the Casimir properties, okay? So let me first show you some of the properties of this model fluid that we were considering. So essentially, it's a binary liquid mixture, like I told you, and the interaction potential is just an usual Lennard-Jones potential. So you have sigma over R12 and sixth term. So this is the model fluid, and now in order to study different static and dynamic properties, the method you follow is the following. To equilibrate the system and to study the static properties, what you do is the Monte Carlo simulation in the semi-grand canonical ensemble. So in the semi-grand canonical ensemble, you basically allow for some A particles to be converted into B particles and vice versa, okay? Which means that when you take into account the Boltzmann factor, in addition to the usual delta E which appears there, you will have a chemical potential appearing in the Boltzmann factor as well. So this is a standard procedure which is known as Monte Carlo simulations in semi-grand canonical ensemble, and if you do that, you get the equilibrium properties of the fluid. Now, once you know the equilibrium configuration from this Monte Carlo simulations, you put it as an input for the molecular dynamics simulations. And in the molecular dynamics, as we know, you just solve Newton's equations of motion using particular algorithm. So we use the velocity-Verlet algorithm. And during this MD simulation, you record data for all the transport properties and you calculate different transport quantities, okay? So the first thing that we look at is the phase diagram of the system, because you have to pinpoint the critical temperature. Now, in order to do that, once again, what you do is that while your MC simulation is going on, Monte Carlo, you record the number of the concentration of A and B particles, and from that you get the information about the order parameter, which involves the XA and XB. Yeah, and the way we quantify the critical temperature is something which is known as the Binder-Cumulant method. So maybe I just tell you what it is. Okay, so this is the estimation of TC. And this Binder-Cumulant, say ULT equal to minus okay, and this quantity is known, its limiting behaviors are known, how it should behave when T tending T equal to 0, and how you should behave in the disordered phase as well. Okay, now this one? No, this one? Yeah, 5 to the power 4. 5, 4. I wrote something else there. Yeah, phi is the order parameter. This is deviation from Gaussian. Yeah. And now the key concept here is basically finite size scaling. And so throughout my talk today, I'll be using a lot of finite size scaling analysis. So maybe it makes sense to explain you how it comes here for the case of Binder-Cumulant. So the rest of the cases, I will not explain it. So what do we mean by finite size scaling is basically has something to do with finite size effect. What it means is that if you look at the properties of all these static quantities, say the correlation length, I'm looking at it as a function of the reduced temperature, I know that it should exhibit a power law behavior with a certain exponent, yeah? Now when you are doing simulations in a finite system, you know that the correlation length is limited. It cannot exceed the system size. So because of that, if you look at its property in a finite system, you will observe a rounding off, okay? And this is something which is known as the finite size effect. So the question is, when you are doing simulations with finite systems, how can you extract information about the thermodynamic system? So for that, people use a technique which is called finite size scaling method, okay? Now, okay, can do it here. So let's try to see how this quantity looks like. Let's do a finite size scaling analysis of it, okay? So let's say that, let's have a look at this thing, say phi power, any arbitrary power k, and that average of it will be nothing but phi power k. Then we will have the probability distribution of phi d phi, which you can write as phi power k, L power beta over nu. I will explain it. Now the p tilde is a finite size scaling function where you will have dimensionless scaling variables d phi. Now let me tell you how you get from PL as a function of phi to P tilde as a function of this thing. That's because we know that if we look at the order parameter, it goes as phi power epsilon power beta, right? Which means that the correlation length power minus beta over nu, and then we know that close to the critical temperature, so basically the system size will, it will scale as the system size, which will give you L power minus beta over nu, which means that if I look at phi times L power beta over nu, this quantity is dimensionless. So that enters as a dimensionless scaling variable here. In addition, you have the L over xi, which is also dimensionless. How does this appear? Because remember, the temperature effect appears via the xi here. Okay, so that's what is the finite size scaling function. Now, if you do a little algebra, say, let's put this phi L power beta over nu equal to x. If you do that, you see L power minus. So it's just variable replacement. If you do the simple calculation, you will find okay, let me just write the final expression. Nu times xk, the distribution function, and this quantity, let's call it the finite size scaling function for this phi k, which is a function of L over xi. Note that the x has dropped out here, yeah? So, what it tells you is that if you look at the kth power, it's L to the power minus beta k over nu times the scaling function as a function of L over xi. Okay. So if you put k equal to 1, you easily obtain phi. It's going as to the power minus beta over nu, then the scaling function. Okay, now the thing is, so if you use this formula, basically note that here in this case, we had the fourth and the square terms. So if you do that, what you see is upstairs, you will have a term which will be minus 4 beta over nu. And downstairs also, let's remove the 3 here. So you will have minus 4 beta over nu by 2 square. So these two cancel out. And finally, what you have is something like this. It's just a ratio of 2 dimensionless scaling functions. Okay, so what does this mean? It means that if you look at this quantity, which we define there, which is known as the winter cumulant, it doesn't have any L-dependent prefactor, okay? And these terms are actually dimensionless. So this UL of T, it depends on only the ratio L over xi, but it does not depend on L. Now, when the temperature is close to the critical temperature, which means the correlation length is becoming large, infinity, it means that this U here, U of T, it doesn't depend on L any longer, right? Because there is no L dependence. So that's why let's drop out the L here. And so it basically takes a constant value. What it also means is that if I now plot, say this U as a function of temperature, for different system sizes, there should be one temperature at which all the curves for U must cross each other. Yeah? And that temperature is nothing but the critical temperature. Okay? so that's the main logic behind this Binder Cumulant exercise, that you calculate this quantity for different system sizes, finite system sizes, and you plot it as a function of temperature. Because of finite size scaling, which is coming from this correlation length diverging at T equal to Tc, at one point they all should cross each other, and that's how you will get the estimate of the critical temperature from the simulation. Yeah, so I'll just show you the plot from the Monte Carlo simulations. Can you go to the fourth slide? We just okay. Mm-hmm. Okay. Yeah. Thank you. Yeah. So that's what is being shown here. So different colors correspond to different system sizes, and as you can see that at a certain temperature, which is the critical temperature, they all cross each other. This is just a zoomed in picture, and so from this exercise, you extract the value of the critical temperature. Okay. So now once you know the value of the critical temperature, the next job will be to calculate, quantify the critical behavior of different transport properties and different static properties. In particular, the quantities which we are interested in are the bulk correlation length and the static structure factors, okay? This will be important because the bulk correlation length is the thing which determines the surface adsorption width. So, so this is crucial. Now, as I told you before, the bulk correlation length, it exhibits this critical singularity, okay? So the idea is the following: you calculate this quantity, and then if you plot it as a function of the reduced temperature, okay, so first of all, you see that as you are approaching closer and closer to the critical temperature, the correlation length is increasing because of the critical enhancement effect, and different colors here correspond to different densities, and we needed to do it with different densities because this was relevant for the study of Casimir forces. So, I mean, if you want to study Casimir, you need to have a fluid which will have very large correlation length. So we needed to do it for different densities, and as you see, as the density decreases, the correlation length value also decreases, and as the density increases, and the solid lines here are the predictions from the theory, and in the temperature regime which is unaffected by the finite size effect, you get a nice matching with the theoretical the prediction. Considering the known value of nu, you get the value of the critical amplitude, okay?
How did you get the value of size?
Huh?
How did you get the value of the correlation length?
Oh, that's from the structure factors, yeah. Okay, so let me now show you the results for the static structure factor and why is it important. So basically, if you are considering a binary liquid mixture, we know that there are two fluctuating fields. One is the partial density, and the other is the concentration fields. So I mean, you can write it as, say, if rho is the total density, the fluctuation of that can be written as alpha here corresponds to, say, the alpha species, and this is the average, which you can also write as n alpha by the volume plus and now, similarly, you will have fluctuations of the concentration. Let's call it C, which will be given by xp times and if you can decouple these two fluctuating fields, you can write down expressions for different partial structure factors, and those structure factors actually come from the Fourier plane. So I'll just write down the expressions here. So these are just the corresponding things in the Fourier plane. And as you can see, you can have either concentration, concentration, or density, density, or density, concentration things. And okay, now the thing is you can define static structure factors. Things which are important here are the density, density, which is defined as similarly, you will have concentration, concentration, which will be more important here if you are having a binary liquid mixture. Remember that for a single component fluid, where you have a vapor-liquid transition, it's the density which will be the relevant field. But if you have a binary liquid mixture, it's the concentration field. Okay, and then let's skip the rho C part here. Now, we are interested, like I told you, in the concentration, the critical concentration fluctuations, which are borne out by the CC. And you can get the extended Ornstein-Zernike form of this CC, which is given by rho kBt times the chi. Chi is the susceptibility by 1 plus k square, square, it's the bulk correlation length. This is valid for to sigma. So you see here that it actually defines the static susceptibility as well as the correlation length, whose critical behaviors I already note down there, okay? Now, so what we want to do now is to look at the properties of these two quantities, the density, density, and the concentration, concentration structure factor for different densities of the model fluid. So first of all, okay, let's first have a look at the open symbols. The open symbols correspond to the density, density structure factor. As you can see, for the entire range of the K sigma, which is considered here, and different temperatures, which are marked by different colors, you don't see any prominent critical enhancement of this quantity, even if you approach close to the critical temperature, okay? So that already tells you that probably the density, density fluctuation is not important here. And now if we look at the structure factor for the concentration, concentration, so the green one corresponds to the temperature which is farthest away from the critical temperature, and in this direction we are getting close to the critical temperature, okay? So as you see that as we are approaching the critical temperature, the magnitude of the structure factor here, so that increases, which already talks about the enhancement of the critical composition fluctuation. And then finally, the black data, which corresponds to T equal to Tc, you see that it nicely matches with the theoretical Ornstein, extended Ornstein-Zernike form for almost a decade in the K sigma, which is, by the way, quite difficult for MD simulations to obtain. So this picture already gives you an idea that for the particular density that we are working at, we are already far away from any kind of liquid vapor transition, because the rho doesn't show any critical enhancement. And that is needed because if you have a binary fluid, you might have a situation that there might be some kind of liquid gas transition as well, but we have to be far away from that. And the second picture here corresponds to the density-density structure factor as a function of different overall densities of the system. So as you can see, for the highest density, you don't have any critical enhancement. Then as you decrease the density, beyond a certain density, basically the critical enhancement effect creeps in, and which you see from this part here. So this picture already gives you an information about which density range you should work on if you want to study different properties of this binary, confined binary liquid mixture. Now, yeah, I mean, we also look at the properties of different transport quantities, But for the timing, I'm thinking now I'll just skip it. So if we have time at the end, maybe I'll then come back to it later.
This exponent value that you wrote down, your own work or?
No, the exponents are, we take from the Ising universality, and just the amplitudes are.
What I was getting at is that this gives you accurate values of the exponents, this sizes that you looked at.
Yeah, that we did from a finite size scaling analysis. So there, if you keep it as a variable, you see that the data collapse, yeah. Okay, so now, so having...
These are the best values known for Ising.
So, I mean, there is a review article by Palacetti, I think 2002. Those are the values he mentions there.
Do you know how they get those values?
Some are from Monte Carlo simulations. Ising, yeah, Ising model. And
you think you can kind of get those? Right?
Yeah. So,
But how close does it get?
So, okay, I don't have the plot, but I mean,
Maybe not. Take the minus 2 plus eta, must have taken some value of eta. So
yeah,
from,
that we take from the literature, yeah.
Finite size scaling is fixed just the TC, is that correct?
Finite size scaling, sorry.
Finite size scaling analysis, you fix TC, is that correct? Or?
Yeah.
TC is one of the things, but also you get the
Also, you get the, yeah.
You get the exponents, right?
You get the exponents, yeah. Exactly. Okay, now yeah. So now once you understand the properties of this bulk fluid, you know the value.
The accuracy of the
Yeah, so I mean, the critical temperature you can estimate quite accurately. It's up to the third. Right, right. And so the, I mean, that's why the common practice in the literature with simulations is that you take the exponent from the literature, okay?
I mean, you have your data
And
still find it.
yeah, yeah. And right, so
how sort of involved would your limits have to be to, for example, get to the third place of this?
so the best way to understand that is to do the finite size scaling, and what we get from there is, I don't remember the percentage, but if I remember, it was quite accurate up to the third decimal place. But if you know the exact number, I can look into the paper and this, yeah.
to that level of accuracy.
Exactly, yeah.
So I guess what they're asking is that how big your simulations is.
So that's okay, okay. Those are for about 1 lakh particles. So it's really big. Then, yeah, exactly. Okay, now the thing is, so if you take this same binary liquid mixture and put it into confinement, like I told you, the surface effects are going to come into the picture, okay? And what is worth mentioning here is that those surface properties are quite well understood for the equilibrium situations, the static properties. But if you want to look at the non-equilibrium dynamics, it's not so well understood. At the kind of singularity that appears on the surface, that depends on the boundary condition which you put on the confining surfaces. So basically, if you take bulk fluid, which say belongs to the Ising universality class, and if you are close to the critical temperature, you will see that every bulk universality class gets separated into different surface universality classes depending on the surface boundary condition that you put in. Now, why does this become important? That's because if you think about it, let's say, for example, talk about a lattice system. So the spins, which are on the surface layer, okay, they are going to have lower energy because of the missing neighbor effect as compared to in the bulk. Okay. Now, one way to overcome it is to increase the coupling, the spin coupling, by a certain factor related to the bulk. Okay. And if you do that, so let's say that we increase this coupling by some lambda. Okay. Now, depending on the value of lambda that you take, you get situations where which will determine if the fluid or the spins on the surface get ordered, even if you have the bulk fluid which is not ordered, or say on the other hand, if you are looking at the system as you are approaching from the bulk, whether the ordering is getting more and more enhanced, in which case you will have a surface adsorption layer, or it goes the other way around, which is basically for the magnetic fluids. So for every dimension, let's say for for every dimension, there is a critical value of this coupling strength. And if it is greater than this, the critical value or not, depending on that, you get different surface universality classes. If it's very large, you get something which is known as the normal surface universality class. The key feature of that is that if you are looking at the fluid, as you are approaching the surface, the ordering is getting more and more pronounced. And in this case, you can have ordering on the surface layer, even if the bulk is in the disordered phase, okay? So that's a characteristic of the normal surface universality class. You can also have something which is known as ordinary surface universality class, which is common for magnetic systems, and in this case, it goes down. Now, if you actually remember the things which I was telling yesterday, in the surface free energy, we had C psi squared d psi minus H psi d psi. We took surface free energy like this, right? So this term C here, which appears, this is nothing but proportional to this lambda minus lambda C, which dictates how strong the ordering is going to be on the surface. So I mean, these are basically the properties of different surface universality classes, but if you take a liquid, for liquids, which is important is always the normal surface universality. Because the wall is in generic situations, it's always going to attract one of the two species, and so you are going to have more ordering and a surface adsorption layer. Now, the question is, how do we characterize the behavior of these surface properties? So one way of doing that, which is typically followed, is to look at the laterally averaged order parameter profile, which is, it's a very local quantity, which is the difference in the concentration of the number of these A and B particles. Okay. And now let's see how the scaling is going to behave if you have the surface. So we know that if we are in bulk, it goes as phi 0 epsilon power beta. Now let's say we take a semi-infinite system, which means that we have only one wall. In that case, this order parameter now will depend on the perpendicular distance from the wall. That's why the Z comes in, and of course temperature, like it was in bulk also. We have epsilon power beta. And now a scaling function will come in because you have the surface here, and the scaling variable, once again, Z over xi, so Z is basically in the perpendicular directions. And so through xi, basically this temperature dependence comes into picture. Now, this scaling property, if you have a semi-infinite wall, this is well studied in mean field theoretical calculations as well as RG theory. But if you take now, instead of one surface, say if you take two surfaces, then as you can see, this growth of the correlation length, that is limited by the separation distance between the two surfaces, right? So you will have one more scaling variable which will appear into the scaling function. So then what you have, it will depend on Z, T, Now the new variable will be d equal to phi 0. We will see what to put here, and the scaling function, which will now depend on z over d and d over xi. So the temperature dependence comes from xi once again, and this z over t, that will dictate basically depending on the thickness of the slit, how the properties are going to change. So what will happen here is that the d should enter here, and it will basically be that d over xi 0 power minus beta over nu. How do you get from epsilon power beta to this one? That's because this epsilon power beta, you can write it as xi power minus beta over nu in terms of correlation length. And now let's make it dimensionless, because this is dimensionless, so we have to make things dimensions match. So you put it as xi power d times beta minus beta over nu. So if you do a finite size scaling, basically this is the scaling the formulation that one comes up with. And now the question arises, what are the properties of this scaling function which is involved here? Because that will tell you the properties of the surface adsorption layers which are forming. And as far as the property in case of a slit geometry is considered, this is known only for the large surface strength limit, and it comes from mean field theoretical calculations using Ginzburg-Landau free energy within the model B dynamics. So I'm just thinking whether to tell you the properties which comes from the model B dynamics. So how much time do I have? Can I take 5 more minutes? Yeah, okay, good. Okay. So these calculations, these studies are also quite new, because if you look at the standard literature, all these calculations were used to be done in the grand canonical ensemble, where you don't have any total number conservation constraint. But if you take a binary liquid mixture, you have this additional constraint imposed, which is that the total number of A and B particles have to be constant, and that makes things different. So in the mean field theoretical calculation, what they do is they start with the usual free energy, dz. You will have the term, then the bulk free energy, which is, let's say, r by 2, the phi square, phi 4 term. This is the standard method. Then you will have a surface contribution. Now, for the surface contribution, it's written as, let's skip this half, so c phi square minus h times phi, and this is what I was using yesterday also. And now we have two walls, and the thickness is d. And if you have mean field theory, you know that you know how this r and g, how they are related to the correlation length. So these things are quite well known. Epsilon. And as you see, these amplitudes are once again non-universal. And this C is called the surface enrichment parameter, and H is called the surface adsorption strength. Now, if you want to look at the dynamics of the system, that's given as, you will have a diffusivity term, and then this is the usual formulation which one does considering the current. So it's the same as the approach which was I was using yesterday. And so then you can write down the expression for the chemical potential and all. So I'm not writing that. I mean, you know that if you're starting from the free energy, you can get the chemical potential, which is del F del psi. And now the idea is that if we want to have an expression of the static surface profile, you have to minimize this total free energy, okay? And when you do the minimization with respect to the boundary condition that the total number of particles equal to some constant, and you take into account the boundary conditions that on the left-hand side, you have this surface property and the same on the right-hand side, you solve those equations basically, and what you get is the expression for the order parameter, and it goes as cos hyperbolic z root epsilon by sin hyperbolic b root epsilon by 2. Okay, so this expression, I mean, this finding is also quite new. What it tells you is that if you are at a fixed temperature and you are looking at the functional form of this order parameter, it behaves as a cos hyperbolic function. But this is, once again, it's purely mean field theoretical calculation. And to do that, oh yeah, I forgot to mention, to do these people also ignored the fourth order term, okay? So it's mean field theory as well as the linear approximation. And question is, of course, if you are having critical enhancement effects as well, which is what you will get if you are doing MD simulations, is it still going to be valid there? Yeah? And yeah, so I mean, you can also show that the limiting behaviors of this scaling function or the order parameter profile, it will behave as an exponential function, exponential minus z over xi, when the distance is quite far away from xi and very close to the wall. It behaves as in a power law behavior. So let's say that we have the wall here and we have the fluid. You will have a thin, a small region which is of the order of, say, the particle diameter, okay, the microscopic details, and in this part, it's going to be purely non-universal. So the scaling property that you look at, that's going to be valid only if you are sufficiently far away from the surface, okay, such that the microscopic details don't matter. What dictates there is the correlation length, but you cannot be very far away from the surface as well, that all the effects from the surface are already gone. So you have to judicially choose the region where you are going to see the effects of these things.
This would be d over sigma of the order of R3.
Huh?
So this constraint,
yeah,
in terms of d over sigma,
yeah,
would be of the order of, I mean, how many layers of it? Okay. I mean, this constraint that you said that if it's
this you mean? Yeah. This you mean? Roughly 2 molecular layers. Yeah.
And far away would be?
So if you are very far away, it will then just decay exponentially.
Right.
So far away would be like, say, if this is around 2 layers.
Because this is what of the order of 3, 4 or something.
No, so by far away, I mean around, say, 40 molecular layers.
Yeah, no,
yeah.
But in your MD setup,
you're
typically considering d over sigma to be of the order of what?
D over sigma, 40. Roughly, yeah, yeah. So you will have a part which is non-universal, then you will have a region where it behaves as the decays as the power law, and then you will have the exponential regime. And people also study how this crossover happens depending on which surface strength you consider, which temperature you consider, and so those are called basically bulk to surface crossovers. Yeah, so
you have actually done this in your simulation. You have some thoughts of how?
Yeah, some, yeah. Okay. Yeah. So here, you have the walls here, okay? You have a Lennard-Jones liquid here, and the walls are attracting only the A particles of the, preferably the A particles of the binary fluid by once again a Lennard-Jones interaction. And then you look at the laterally averaged order parameter profile, okay? So these things, different colors here correspond to different widths of the slit. And they are all at fixed temperature, which is the critical temperature, bulk critical temperature, and the same value of the surface interaction strength. So first of all, as you see, if the slit width is narrower and narrower, this depletion layer, it becomes much more thicker, okay? And that has to do with the fact that the total concentration of the system is 0, which is the constraint that I was talking about, that if you impose the constraint of total mass conservation, the properties of these order parameter profiles, they change rather than from a single component fluid. So it does exhibit some kind of slit width dependence in terms of the thickness of the depletion layer, but if you look at it, the magnitude of the order parameter, it doesn't really much depend on the system's the separation distance. That's because this is given by the surface strength, okay? So the H1 which appears there. Now, if we look at the density oscillations for this system, so this is the same oscillation that we were talking about yesterday. So very close to the surface, you have these strong oscillations, and then it exists, but then if you are far away, the magnitude is really much smaller and smaller, and the density is close to the bulk value in the middle of the slit. So here I plot the order parameter profile for two temperatures. The red one corresponds to the bulk critical temperature, and the blue is far away from the critical temperature. So as you see, at the critical temperature, first of all, it crosses over to the negative value at a much larger distance, and that's because this is dictated by the correlation length, okay? And it also measures the width of the surface adsorption layer. And since at critical temperature this is larger, so it crosses over at a much larger distance. And then the magnitude in the middle of the slit, the depletion layer, that's also much larger as compared to the high temperature. And that has to do with the fact that the total concentration has to be 0. Now, the thing is, so now let's think about scaling. So all these plots that I was showing you, these are for different system sizes. So the question is, the same kind of scaling analysis that I was telling you, does it apply here? And okay, so I rubbed it off, but so you have the order parameter, yeah, and then it goes as phi 0, and you will have d over xi 0 times minus beta over nu, and then the scaling function. And in the scaling function, you have two variables. One is d over xi, and the other is z over d. So it's a function of two variables. So one way to plot it is that you keep one of the variables, fix it at a constant value, and plot as a function of the other variable. So that's what we do here. These data are all at the critical temperature. Wait a minute. Yeah. So these are all at the critical temperature such that this one becomes 0, and then you plot it as a function of the other scaling variable. And as you see here, for almost the whole range of this slit width, you see a very nice data collapse. So different colors correspond to different system sizes. And if you plot this scaling function, that's what is being plotted here, as a function of the scaling variable, one should expect data collapse if it holds, right, with the correct exponent. Now, the thing is, if you are very close to the slit here, okay, you see that here the data for different system sizes don't really fall on top of each other, and that's because this is the non-universal regime. And it's in terms of z over d, but if you calculate in terms of molecular layering, you see that it's almost of the order of 2 molecular layers or so. But once you are away from that, you see a very nice data collapse for these critical behaviors. And one thing to point out also is that this holds only if you have very large surface strength. Okay? If you have finite surface strength, then that will enter as another scaling function. Okay, now let's talk about the dynamic quantities. So why is it important in dynamics is because the surface effects that will propagate from the surface into the bulk. So if I say pick up any point on the bulk, and if I look at how the order parameter in the bulk is changing as a function of time, let me just write it down. So now we are talking about dynamics, yeah? Surface. So let's say I'm looking at the local order parameter as a function of time. Okay, how come the time enters? It's such that, let's say that initially at time t equal to 0, my system is in the homogeneous phase at a temperature far above the bulk critical temperature, such that if I look at the order parameter profile, it will have almost a flat profile, okay? And then I quench it to the critical temperature, which means that with time, I will have these surface adsorption layers which are developing. They will become more and more pronounced as time progresses. And the question is, how does it evolve with time? So if you look at the value of the order parameter at any distance, say any distance z, as a function of time, you will see that it depends, the property depends on the distance from the wall. If you are in the middle of the slit, which means it's behaving like a bulk, it will decay with an exponent which is governed by the bulk exponent. And if you are close to the surface, you will find that up to a certain distance, the order parameter profile will behave with the bulk exponent, then there will be a crossover, and it will behave with an exponent which is dictated by the surface universality class. So clearly, when you have this non-equilibrium dynamics going on, the surface effect, it takes some time to propagate into the fluid. And what we are interested in here is to study, if I look at the value of the order parameter on the surface of the fluid, which I call phi 0, how does that evolve, how does it change with time? And so there are mean field theoretical calculations for this time dependence as well. Those are once again using the Ginzburg-Landau free energy and in the linear approximation that they don't consider the phi-4 term. And so the approach is same that I was describing before. You start with the Ginzburg-Landau free energy and then you have the time dependent equation and you just have to solve the equation. And it's possible to solve it analytically only if you ignore the fourth order term. And what they show. This one? Yeah. Yeah.
So why is it large?
Okay. So the initial state is that my system is far, far away from the critical temperature. It's still in the slit geometry, but it's far away from the critical temperature. So I will have a small surface adsorption layer, but it's really very small as compared to the critical temperature. Then at t equal to 0, I quench it to Tc. So then as time progresses, this adsorption effect will grow on and you will have the surface effects. Okay, and then what we are now interested in is that if I look at the property of this order parameter on the surface, how does that change with time? And it was predicted from mean field theory that it goes as t to the power 1 over z, where z is the dynamic critical exponent. And okay, so this is valid in a short time regime when it's less than a certain critical time. And what do I mean by that? I'll explain here. So anyway, the prediction is that it should grow as a power law behavior with an exponent 1 over z. But this is valid for the model B dynamics. So what we look at here is, so that's what is plotted here, okay? Now you see that at very early time you have, this is once again a non-universal regime. And then beyond a certain crossover time, you see this 1 over z power law regime, okay? So that's the way it's growing, the order parameter profile is growing. And now one is interested in looking how is it saturating to the equilibrium value. So this is as a function of time, okay? So it starts at t equal to 0, non-equilibrium, it increases, and then gradually it will try to saturate to a steady state value. So now let's ask the question, how does it saturate to this equilibrium value? Okay, so that's what I show here. And then it turns out that if you look at its saturation, first it follows a power law behavior with a certain exponent, and this exponent turns out to be different for model B dynamics and the model H dynamics. So it goes on up to a certain time, and beyond the crossover time, something very interesting happens. And what happens there, beyond this point, you will see that this quantity, phi 0 as a function of time minus the phi equilibrium, that decays in an exponential way. So the power law behavior which we were observing there, suddenly now it has crossed over to an exponential regime. And why does that happen? That's because when you see the exponential regime, it means that the effect from the second surface here has now propagated close to the first surface. So even though you are calculating the order parameter on the first surface, its behavior is now going to be coupled to the dynamics at the second wall as well. And this is also the times when the dynamics in the entire system has become coupled and the Casimir forces become important. So in this case, you don't see the exponential behavior because the slit is large, but if you take a very small slit, you do observe the exponential behavior. And in order to quantify the dynamics in further detail, what we also look at is something which is known as this, the correlation, the cross correlation. So I have two walls here. Let's say this is the first wall and this is the second wall. If I want to see how the dynamics, what is happening at these two walls depend on each other, a relevant quantity to study is the cross correlation. So let's define it as, say, the order parameter on the first wall at time t minus the average. So it's the usual definition. And then the second wall. These averagings are over initial configurations. So if you look at this quantity now, you see that, remember the starting point is a very system with at a very high temperature, which means that these two walls are not correlated at all, okay? The correlation length is very small. So that's why the cross correlation is 0. It starts from 0. Then as time progresses, correlations are developing in the system, so it's increasing, and then finally it saturates to a plateau value. What it means is that the information it gives you is that beyond a certain crossover time, the two slabs here, the two walls have become fully correlated. That's the time you see the exponential, exactly, yeah.
Why should it be exponential?
I mean, it comes from this calculation, mean field theoretical calculation. The physical picture, if you ask me, the hand waving argument is that now because things are really coupled, it's changing much faster. But of course, that's not a concrete understanding. Yeah. So.
Exponential have also time scale. So how does the time scale come about? Exponential in time, right?
Exponential in time. Yeah.
There is a time scale at different time.
Yeah.
And that depends on the separation.
Exactly. Yeah. No, I think. So if you look at this exponential, the term which appearing is pi square d square t. So I believe the crossover time will be proportional to 1 over d square Yeah. This is the slit width. Yeah, yeah. Yeah. Mm-hmm.
There has to be some other dimension of that.
Ah, so, right, yeah. Diffusivity, no. Yeah, you're right. Something's to here.
But basically it's 1 over d squared.
Exactly. If you take large.
It's so strict. So when d is large,
This is only true at large. Yes. It's outside.
Yeah, so. Okay, so now, as you see, if you are at a very late time, these two walls are now getting correlated, and which means that the things which are happening at the first wall are now being affecting the second wall as well. So each wall now feels the presence of the other one. And if you have a situation like that, so when this cross correlation has already saturated, you can write down the total. Okay, so basically that's the time when you have the Casimir forces which are acting into the system. Okay, so what do I mean by that is that if you look at the total free energy of the system, you know that you will have a bulk contribution, then you will have a surface contribution which is coming from the missing neighbor effects of these two walls which were there. So it's basically twice, and then you will have an excess contribution, and this excess contribution, it turns out that it tends to 0 when you have the separation distance between the two tending to infinity. Okay, now, and so this is what gives rise to the excess contribution, which is known as the Casimir force, and one can also calculate the pressure by taking the derivative basically. And so if you do it, it turns out that the total pressure can be written down as a combination of the background pressure, which we call PB, plus the Casimir contribution. And how does this Casimir force or the Casimir pressure behave? So it's known mainly, once again, for parallel walls, for slit geometry, in the limit when the surface field is very large, tending to infinity, and for an aspect ratio, which is very small. And there it's known that it grows as x squared e to the power minus x. Okay, but okay, let me just see it. Okay, so so now the idea is that to look at the properties of these Casimir forces in a binary fluid mixture, and in terms of MD simulations, because the final goal is to look at the dynamics. But then, as it turns out, it affects the static properties as well. So this Casimir pressure, it exhibits a scaling behavior in the sense that you can get as kVt by d cube, and then you have a scaling function which comes into the picture. So this is, I mean, you can, it comes from RG calculations, but you can understand it dimensionally. So this is pressure, this is energy per volume pressure, so this is dimensionless, and it's a function of a dimensionless scaling variable L over xi. Okay? Now, this L over, the behavior of this scaling function as a function of this L over xi is known, and it's known to be exponential function. So here we check that with two different boundary conditions. The first one, we call it the antisymmetric boundary conditions, which means that I have these two walls, and if this wall is favoring the A type of particles, the second wall is favoring the B type of particles, okay? And in such a situation, you do MD simulation and you calculate the pressure from the stress tensor, and once you know the value of the pressure, you can then calculate the scaling function, okay? Yeah, so I'll skip the details of the calculations. If you are interested, then I can tell you. So different colors here correspond to different slit widths. So the L is essentially my D, which I'm calling D here. And as you see, if you are plotting it as a function of the correct scaling variable, you see the very nice data collapse. And on the semilog plot, it turns out to be really exponential, which is in agreement with the predictions from theory. Predictions for the grand canonical ensemble. Now let's have a look at the symmetric boundary conditions, which means both are favoring A type of particles. And then as it turns out that in this case, the scaling function turns out to be positive, and this is quite striking because if you look at the existing literature, the predictions were that it has to be negative, that it's attractive, yeah. So the question is, why is it that something which was predicted to be attractive has now turned out to be repulsive? And the reason there is because of, once again, the constraint, the conservation constraint criteria. So the earlier predictions were in the grand canonical ensemble, but these calculations that we do here, these are in the canonical ensemble. And these are in finite systems that too close to the critical temperature, so the ensemble equivalence need not hold. And it turns out that the things indeed become different. And yeah. So basically then, that's what then gives you an understanding of the static properties of these Casimir forces. And then next one would like to calculate different dynamic quantities. And
so depending on the ensemble that you're working in, the sign of the forces changing,
Yeah. So that
you were yesterday describing these experiments that your colleagues and stuff are doing. You were talking about, oh no, that was this. But if you were to first experiment, what would you observe? Firstly, what would be roughly the magnitude of these? Must be very small forces, right? I mean, is it femto, pico, and minus 12? How would you even measure?
Yeah. So the way they exactly, I mean,
is it of that order?
It's very small, yeah. And so that's why it's difficult. It's difficult to measure in the experiments as well. And another problem is in experiments, if you put two walls, it's very difficult to keep the walls really parallel. And because these things it requires high precision, so in that setup, doing the experiment is really like horrible. So what they do in most of the cases, they take a colloidal particle and they put it to the surface.
So it's a sphere, so you're close enough, so curvature goes distributed. Okay, so in that case, are any of the suppose there was this experiment, so I'm just slightly asking since this thing changed signs, and are there measurements of these forces in a setup similar to the one that you're studying? And in that case, is it attractive or?
So in that case, yeah, it will be same because remember that what do I mean by canonical, grand canonical? It ultimately boils down to the fact that you have a conservation of the total mass or not. So if they are also taking a binary mixture and they are putting it in a chamber in such a way that nothing is going, and so then.
No, I think it's a question of whether you, this is what Abhishek was asking at the beginning. If you have two plates and you immerse them in a
beyond the place, if there's
outside also there is a liquid. So there is an exchange of liquid between the inside and the outside. Then it becomes grand canonical.
Then it becomes grand canonical.
So I mean, you're saying that, but in simulation, I think you just take the two plates and then like you're boundary.
Yeah.
So it's not grand canonical, right?
Not for the whole thing.
Not for the whole thing. No, here the particles are not. There's no fluid outside the walls.
Here it is
exactly.
Because it doesn't.
Because it,
Doesn't go out. The region between the two.
The region between the two, yeah.
But in the experiment, it is grand canonical, right? The one you just described.
Yeah, the one described is.
Described with the colloid, there it's grand canonical, right? Because you're inversing the colloid.
There is grand canonical. Yeah, exactly. So, yeah, and so then the next thing that one would be interested is to look at the dynamics, okay? And in principle, you can I mean, not in principle, what is also interesting is to look at the dynamics of the Casimir force in non-equilibrium situation, like the quench experiment which I was telling you, but that's really difficult. Until now, nobody has really done it. So what we wanted to start with is the equilibrium dynamics, which is comparatively a bit easier to look at. And the thing which we want to study is actually the correlation of these stress tensors. So and then so in this picture, I plot the correlation function as a function of time at Tc for different system sizes, okay? Now, there is a slight mismatch you see here for different system sizes. We will come back to that later. But what's important is that it does exhibit two power law decay regimes. The first one, which is shown here, it's much slowly decaying, and then at very late time, you get a long time tail where the exponent is given by 3/2, and this 3/2, we presume that it's coming from hydrodynamics effects. Now, it's also probably important that I mention here that till now there is no theoretical study as in how the exponent of these correlations should look like. So there are ongoing studies now. So yeah, probably I'll be able to talk about the matching with analytical predictions in a couple of months. So now if you look at this data very, zooming in, you see that it does exhibit a system size dependence, okay? And then the question is, will it exhibit any kind of scaling? Well, it turns out that if you scale it as 1/L, the inverse length, it does then the two curves then just fall on top of each other. So it indicates that this bulk, the Casimir correlation, it is exhibiting some kind of scaling like that. But once again, to tell you that there is no really analytical predictions about the power law, which as in which power of the separation distance it should behave like. So these are some open questions. Yeah, that's T, yeah. Mm-hmm. So, to conclude with, it's to tell you that if you look at the status of Casimir forces, especially the dynamics of Casimir forces, there's really a lot of room to study new things. And the particular problem is, why is it so rarely studied, is because if you look at theory, from theory perspective, it's easier to start with the planar wall. And then they do for the, renormalization fixed point calculations where the surface fields are infinity. Then if you come to experiments, I told you the problems with keeping the parallel walls. And if you have a curved surface, then the property of the scaling function, it's not going to be the same if you have two planar surfaces. So there is analogy, lacking. Then when you come to simulation, that the problem is you cannot really do for infinite surface strains. So these are all finite values. And in addition, you will have a finite size critical temperature as well. So there will be rounding off and shifting. So, yeah. So, to conclude that, so this is basically the status of this Casimir dynamics literature, and new works are being done in this direction in terms of the non-equilibrium dynamics. So, I think with that I will leave it.